Imagine holding a solid steel ball, feeling its weight, its undeniable presence. Now, imagine throwing it at a thick concrete wall. What happens? It bounces off, right? It has to. But what if I told you that deep beneath the Swiss-French border, scientists might have just witnessed the subatomic equivalent of that steel ball phasing right through the concrete? And not just any tiny, ethereal particle, but something much, much bigger. Stay with me, because this isn't just a physics curiosity. It's a discovery that has sent shockwaves through the scientific world, potentially cracking open our understanding of reality itself. We often hear about the Large Hadron Collider, LHC, at CERN, that magnificent 27-kilometer ring where particles are smashed together at nearly the speed of light. Usually, the goal is destruction, breaking particles apart to see what fundamental building blocks lie inside, like finding the famous Higgs Boson back in 2012. That discovery itself was monumental, confirming a key piece of the standard model of particle physics, our best map of the subatomic world. Finding the Higgs was like finding a specific needle in a haystack the size of a galaxy, requiring something like 1 in 10 billion collisions to yield something interesting. It set the bar incredibly high for big news in physics. But recently, a team at CERN decided to do something different. Instead of just smashing things, they set up an experiment to meticulously observe how particles behave when they encounter barriers they shouldn't be able to cross. They were probing a phenomenon known as quantum tunneling. Now, quantum tunneling itself isn't brand new. It's one of the cornerstone weirdnesses of quantum mechanics, the physics of the very small. Think of it like this. In our everyday world, what we call classical physics, if you don't have enough energy to climb over a hill, you simply can't get to the other side. You're stuck. But in the quantum realm, particles like electrons operate under different rules. They exist in a state of probabilities described by a wave function. There's a tiny, but non-zero, chance that this probability wave extends through an energy barrier. So, occasionally, an electron can simply appear on the other side of a barrier it classically lacks the energy to overcome. It sounds bizarre, like a ghost walking through a wall, but it's a real measurable effect. We even use it. Technologies like tunneling electron microscopes rely on it to image surfaces at the atomic level. Certain types of flash memory in your computer use tunneling to store data. So, physicists are comfortable with tunneling for very small particles like electrons. It's strange, but it's known strange. Here, where the CERN experiment allegedly turned the world of physics upside down, the team wasn't using tiny electrons. According to the reports, they used particles that were 1,000 times larger than those typically observed tunneling. Let that sink in. Imagine comparing the size of a single grain of sand to a baseball. That's the kind of scale difference we're talking about, relatively speaking, in the particle world. Classical physics is adamant on this point. Particles that large, encountering a solid physical barrier they don't have the energy to break through or go over, should be stopped. Dead in their tracks. Full stop. It's like the steel ball and the concrete wall, the rules seem absolute. But the CERN experiment reportedly found otherwise. These significantly larger particles were detected passing through barriers designed to be impenetrable to them. They weren't smashing through. They were appearing on the other side, as if the barrier wasn't entirely there for them. This is the core of the shock. It's like watching that baseball phase through the concrete wall. You wouldn't just be surprised. You'd question everything you thought you knew about how objects interact. This result throws a massive wrench into one of the fundamental divisions in physics, the boundary between the quantum world and the classical world. For decades, we've operated under the assumption that there's a fairly clear line. Tiny things, atoms, electrons, obey the weird rules of quantum mechanics, probabilities, superposition, tunneling. Big things, baseballs, planets, us, obey the predictable, deterministic rules of classical physics. But if particles 1,000 times larger than expected can exhibit clear quantum behavior like tunneling, Where is that boundary? Is it less of a sharp line and more of a gradual fade? Does everything, fundamentally, have some quantum nature, even if it's usually impossible to observe at our scale? Professor Brian Cox, a well-respected physicist and science communicator, reportedly suggested this might be the most significant physics result since the Higgs boson. That's not hyperbole. It speaks to the foundational nature of what's being questioned. This also casts a strange light on the Heisenberg uncertainty principle. This principle, a bedrock of quantum theory, states that you can't simultaneously know certain pairs of properties of a particle with perfect accuracy. For example, the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. It introduces a fundamental fuzziness to the quantum world. But how does this principle operate when much larger particles are tunneling? Does the uncertainty behave differently? Does the act of tunneling somehow exploit or even challenge this principle at a scale we never anticipated? Scientists are scrambling to figure out if our century-old framework needs a major update or if we're witnessing a complete breakdown in certain regimes. As if large-scale tunneling wasn't enough, the experiment reportedly yielded even stranger side effects, things that usually live in the realm of theoretical speculation. First, subtle gravitational effects. The instruments allegedly detected tiny, localized fluctuations in the gravitational field coinciding with the tunneling events. This is wildly unexpected. Quantum mechanics and general relativity, our theory of gravity, are notoriously incompatible. Finding a direct, measurable link between a quantum process, tunneling, and gravity, however small, is electrifying. It hints at a possible bridge between these two great pillars of modern physics. This is why CERN is reportedly collaborating with facilities like LIGO, which are designed to detect gravitational waves, ripples in spacetime itself. They need to determine if these faint signals are real or just experimental noise. But if they are real, it could be the first glimpse of the path towards quantum gravity, the long-sought theory of everything that can describe reality at all scales. Second, and perhaps even more controversially, an apparent energy increase. During the tunneling process, the team observed a brief but measurable gain in energy in the particles. There was no identifiable external source for this extra energy. This appears to fly directly in the face of one of the most sacred laws in physics, the conservation of energy. This law states that energy cannot be created or destroyed, only changed from one form to another within a closed system. Seeing particles seemingly conjure energy out of nowhere, even fleetingly, is deeply unsettling and demands explanation. Some theorists are tentatively exploring models where energy behaves differently at the quantum classical boundary, perhaps borrowing temporarily from the vacuum energy of space itself. Others urge extreme caution, emphasizing the need for replication and ruling out all possible conventional explanations. But the data, reportedly robust, is forcing the question. Adding to the intrigue, the team found that increasing the size of the particles further didn't necessarily reduce the tunneling effect as one might intuitively expect, thinking larger things have a harder time squeezing through. The effect apparently remained strong, and in some scenarios, even seemed to propagate through more complex arrangements of particles. This contradicts the standard picture of tunneling as a phenomenon primarily relevant to small, isolated systems. It suggests a more collective or widespread quantum behavior might be at play. This persistence of the effect, even with larger or more complex systems, is prompting physicists to dust off predictions from string theory. String theory is a complex mathematical framework suggesting that fundamental particles are not point-like dots, but tiny vibrating strings. Different vibrations correspond to different particles. Some versions of string theory predict the existence of extra-spatial dimensions beyond the three we experience. Could these larger particles be tunneling not just through energy barriers, but perhaps taking shortcuts through these hidden dimensions? This could potentially explain both the tunneling itself and maybe even the fleeting energy discrepancies, if energy can be temporarily borrowed or exchanged across dimensions. While string theory has historically lacked direct experimental proof, this CERN result, if confirmed, might provide the first tantalizing observational hints connecting it to reality. The statistical significance of the reported data is crucial here. The results apparently pass the 5 sigma threshold. In particle physics, this is the gold standard for claiming a discovery. It means the probability of the observed results being a random statistical fluke is less than 1 in 3.5 million. This high level of confidence is why the scientific community is taking this so seriously, especially given that previous attempts at similar, though perhaps less precise, experiments at other institutions like MIT and Caltech didn't yield these dramatic results. CERN's unique capabilities and the meticulous design of this specific experiment seem to have been key to observing this fragile, large-scale quantum behavior. Okay, so large particles might be quantum tunneling, gravity might be involved, energy conservation might be bendable at tiny scales. What does this actually mean for us, living our lives in the macroscopic world? If this discovery holds up and can be harnessed, the technological implications are staggering, potentially arriving much faster than anyone dreamed. Energy transformation. Forget gradual improvements in battery life. Think quantum batteries. If electrons or even larger charge carriers can tunnel through energy barriers within a battery instead of needing to overcome them classically, charging could become almost instantaneous. Imagine plugging in your electric car and having it fully charged in the time it takes to buckle your seatbelt. Beyond storage, there's talk of quantum tunneling reactors. The idea, still highly speculative, is that by carefully controlling this large-scale tunneling between classical and quantum states, we might be able to directly extract usable energy from the quantum vacuum field itself, the baseline energy inherent in empty space. This would be energy generation without fuel, fission, or weather dependence, fundamentally changing our civilization. Early models hint at efficiencies that would rewrite thermodynamics textbooks. Computing leap. Current quantum computers are powerful but incredibly fragile. They require extreme cold and isolation to maintain delicate quantum states, qubits. Even tiny disturbances cause decoherence, destroying the computation. But if quantum effects like tunneling can persist at larger scales and through barriers, it suggests quantum states might be more robust than we thought. This could pave the way for more stable, fault-tolerant quantum computers that don't require such extreme laboratory conditions. Practical, widespread quantum computing, previously thought to be decades away, might see significant acceleration, potentially impacting drug discovery, materials science, financial modeling, and AI within years, not generations. Some researchers are now talking timelines as short as 5 years for initial real-world applications stemming from this increased stability. Communication reinvented. Today's quantum communication and teleportation are limited by decoherence over distance. Information gets lost easily. But if tunneling allows quantum states to bypass environmental interference, we could see ultra-secure, high-speed quantum communication channels. Imagine sending information encoded in quantum states that tunnel past potential eavesdroppers or noisy environments. This could lead to communication networks that are fundamentally impossible to hack using current or foreseeable methods. Materials science fiction made real. If particles can tunnel through barriers at scale, could we design smart materials that allow objects or energy to pass through them selectively on command? Think of zero-resistance semiconductors, where electrons tunnel effortlessly, eliminating heat loss and energy waste. This would revolutionize everything from smartphones, no more overheating, to power grids and supercomputers. Security and defense paradigm shift. The potential for unhackable communication is obviously huge for governments and military organizations, but it goes further. Imagine quantum radar. Current stealth technology works by absorbing or deflecting conventional radar waves. But quantum radar, potentially leveraging tunneling effects or entangled particles, might be able to detect objects based on how they subtly disturb the quantum field, regardless of their shape or material. Stealth technology could become obsolete overnight. Medical miracles. Consider the blood-brain barrier, a protective membrane that keeps toxins out of our brain, but also blocks many potentially life-saving drugs. Researchers in nanomedicine are excited by the possibility of using controlled quantum tunneling at the nanoscale to deliver medications directly through this barrier to treat brain cancer, Alzheimer's, Parkinson's, and other neurological disorders without invasive surgery or harmful side effects. It could unlock treatments for conditions currently considered untreatable. Beyond the technology, the most profound implications might be for fundamental physics itself. The quest to unify quantum mechanics, the small and general relativity, the large has been the holy grail of physics for nearly a century. Einstein spent his later years searching for it in vain. This CERN experiment, by showing quantum behavior bleeding into larger scales where gravity also operates, might provide the crucial experimental data needed to finally bridge this gap. It could offer the first real-world tests for theories of quantum gravity, showing how spacetime itself behaves at the quantum level. Furthermore, could this phenomenon help explain the universe's greatest mysteries, dark matter and dark energy? These invisible components make up about 95% of the universe's total mass-energy content, yet we have no idea what they are. Could they be manifestations of quantum effects operating on cosmological scales, effects we couldn't previously measure or even conceive of until witnessing large-scale tunneling? Perhaps dark energy, the force accelerating the universe's expansion, is linked to the energy fluctuations seen during tunneling. Perhaps dark matter particles interact with normal matter via unexpected quantum tunneling pathways. The potential connections to string theory and extra dimensions, or the holographic principle, suggesting our 3D reality arises from information encoded on a 2D surface, add another layer of mind-bending possibility. If particles are tunneling through hidden dimensions, it could explain why gravity is so much weaker than other forces, or provide a mechanism for the holographic projection of reality. The patterns observed at CERN reportedly align with some mathematical predictions of these theories, lending them newfound, albeit tentative, experimental weight. So what's the takeaway from this whirlwind tour of potentially reality-altering physics? For me, it's a profound lesson in humility and the sheer, unending strangeness and wonder of the universe. We build these intricate models, these laws of physics, and we become comfortable with them. But reality, it seems, always has more surprises in store. It reminds us that our understanding is always incomplete, that the map is not the territory. This potential discovery underscores the incredible power of human curiosity and persistent inquiry. Scientists at CERN weren't necessarily looking to overturn fundamental physics. They were meticulously investigating a known phenomenon under new conditions. And in doing so, they may have stumbled upon something far more revolutionary. It teaches us to keep questioning, keep probing, even when the answers seem settled. Sometimes, the most groundbreaking discoveries hide in the places we least expect, challenging our most basic assumptions about what is real or possible. For our daily lives, perhaps the lesson is to embrace the unknown with a sense of wonder rather than fear. Our world operates on principles far more complex and interconnected than we often perceive. While we might not see quantum tunneling happen with our coffee mugs, understanding that the underlying reality is fluid, probabilistic, and potentially interconnected in ways we're only beginning to grasp can foster a deeper appreciation for the mystery of existence. It encourages us to stay curious, to keep learning, and to recognize that breakthroughs often come from challenging the status quo. This story is still unfolding, and rigorous verification and further experiments are absolutely essential. But the possibilities are undeniably exciting and thought-provoking. What do you think scientists should explore next with this potential discovery? If large-scale tunneling is real, what other applications can you imagine? Are there ethical considerations we need to start thinking about now? Let me know your thoughts in the comments below. I'm genuinely curious to hear your perspectives. Thank you for joining me on this journey to the edge of physics. I hope this exploration sparked your curiosity as much as it did mine. Wishing you all the very best of health and a mind open to wonder. If you enjoyed this deep dive and want more content exploring the frontiers of science and technology, please consider hitting that subscribe button and giving this video a like. It really helps the channel reach more curious minds like yours. Until next time, keep questioning everything.